So in this final video, we're going to talk about the types of projections and then touch on the projections that we use in South Africa. So to start with, what types of projections do you have? We have conic projections, so we have planar projections, and we have cylindrical projections. And those cylindrical projections can either be transverse or they can be normal cylindrical projections. And we're going to go into the details of all of those. So one thing to keep in mind is, what is a projection? So a projection starts off with what we spoke about a bit earlier, or in the previous videos, which was the shape of the Earth, so the datum and the spheroid. That becomes very important because we need to understand what is our reference in terms of the globe. When we start looking at what I've spoke about, the angular parameters, and this is what is our central meridian. So what longitude are we going to use? What latitude are we going to use as our origin of this projection? What units are we going to use? Are we going to use degrees? Are we going to use a different angular unit? And then in the case of conic projections, what are our standard parallels? So what are the two areas where the lines are going to cut the Earth? And so there's a couple of things we need to take into account. Central meridian, longitude of origin, latitude of origin. And these are these concepts of what is a projection. So everything you see on the screen at the moment defines a projection. And then some of the linear parameters are, what's our scale factor? What's the scale factor going to be? What is our units? Are we meters, feet, etc.? And are we doing a false easting or a false northing? And that is sometimes, in Cape Town, you're about 3,700,000 meters away from the equator. So potentially you don't want to carry the minus 3,700,000. So we could put in a false northing of 3,700,000 and only work on the last couple of digits. So we reduce the size of that number. But sometimes if you don't define that, or if your metadata doesn't illustrate that, it can be sometimes difficult for somebody to then work out where the data is. We're going to talk about that also a bit later. So let's start with these planar projections, or azimuthal projections. And this is where you literally take a piece of paper and you put it onto this round surface, or the globe. And where the paper touches the globe is the origin, so that is the start of the projection, or the center of the plane, as we call it there. And there's a couple of different names for these: genomic, stereographic, orthographic. We don't typically use these in South Africa, but it is something that is out there. The next is conic. So we start looking at a conic, where we take a cone, we take a piece of paper, and we turn it into a cone by folding it, and then we place the cone over the Earth's surface. So there you can see it. It looks like a hat. And where it touches the globe, along these parallels, so where the physical piece of paper is touching the globe is where the concept of the standard parallels come over. And those are typically latitudes. In terms of two projections we use in South Africa, the one being Lambert's conformal conic and the other one being Alber's equal area, standard parallels are very important and need to be taken into account. So here, polyconic, secant conical, central conical are some of the projections. We use a conic projection in both Lambert's and Albers, so we will touch on those a bit later. When we come to the cylindrical projections, and this is where you take a piece of paper and you roll it into a roll, and then you put the Earth in the middle of it. Depending on the orientation, a standard Mercator projection is where the paper is sort of vertical, and if we turn the paper in this direction, then it's what's called a transverse Mercator. So we use transverse Mercator projections in South Africa, and if you look at that comment in the second line, it says it follows the transverse Mercator. The meridian is one of the longitudes, and this is the premise of the transverse Mercator projection, that we have a central meridian, and that follows one of the longitudes. And when we get to the projections used in South Africa, we talk about allozones, and those zones follow these central meridians. So here, transverse Mercator is one of those projections. We have cylindrical, equal area, or Gall's stereographic cylindrical, not used here. We are focused on transverse Mercator. So take-home message: be aware of these different projections. Be aware of the parameters. So datum, spheroid, angular units, central meridian, standard parallels, measure of angle, your reference latitude, reference longitude, false easting, false northing. Those are concepts you need to understand because that's what makes a projection. So when somebody says, what are the definitions of projections? It's the shape of the Earth, what projection you're using, and what are those parameters you're using inside that projection. And now we need to start understanding when are projections relevant. When is it a national projection? When is it a global projection? And when is it a local projection? Because each one of those is different. Moving closer to home, South African projections and some of the official projections and what's happening in this environment and how are we keeping up with technology. So I thought I'd bring in immediately a map. And here's a map of South Africa. It's in geographic. But I've brought and I've put across both allo zones and UTM zones. So you'll note here in allo being the red text and the red vertical lines or longitudes, we have zones going from 17 through to 33. There's 9 zones. And in the case of the UTM zones, which are in blue, we have 4 zones starting at UTM zone 33 going up to 36. So when somebody starts talking, this is a very handy map because if anybody says, I'm mapping Beaufort West, what projection should I use? You can be defining, in this case, it's going to be UTM 35 South, and potentially I'm going to be using allo 21 as an example. So familiarize yourself with this, make yourself a map like this that makes sense. If we start with a term you're going to hear a lot of, LO. It's called the Gauss-Kruger projection, and if we go into the details, it's a south-orientated transverse Mercator. So it's an application of the transverse Mercator where they've swapped the x and the y axis, and they've also negated them. So they've multiplied them both by -1. The history behind this is that we didn't want both our numbers to be -1, so we have used this process to get back to a traditional sort of graph. And this is applicable at a scale of less than 1 in 50,000. So if you're mapping roads, if you're mapping cadastre or land parcels, or mapping anything which has to be very accurate, you need to use Gauss-Kruger. The 2-degree zones, we've spoken about it earlier, a 2-degree zone equates to about 200 kilometers. And here we talk about 17, 19, 20, 21, 23, right through to 33 on the coast, on the east coast of KwaZulu. We talk here about westings and southings. So if you ever hear that term, you must know this is a traditional allo coordinate system. And the scale is consistent along that central meridian, and it gets worse as it moves away in east and west. But you only can move away 100 kilometers in either direction. So you are very limited in the application of this projection, but it's very, very, very accurate in that environment. Now, across the world, they do not use Gauss-Kruger, and they don't use what we traditionally use as the allo. We use the projection called transverse Mercator. And what is the difference? It's exactly the same projection system. However, we have not negated the x and y, and we haven't swapped x and y around. So you might one day get a data set where the y numbers look like x numbers and the x numbers look like y, and they seem to have wrong negatives. There's negatives in front of them. Then be aware that that data is a data set coming from Gauss-Kruger or allo. And however, most of us are using the same concept, but we are just using a traditional transverse Mercator. So here, once again, 2-degree zones, 9 of them across the country. But we talk about not westings and southings, we talk about eastings and northings. So if you hear those terms, be aware that one is allo and the other one is transverse Mercator. And then the scale is once again consistent down the meridian, and it moves away up to 200 kilometers, 100 kilometers on either side of the central meridian. The other projection system inside of that map was UTM, or Universal Transverse Mercator. And what this is what they've created a projection which allows you to do something very similar, but instead of being limited by 100 kilometers on either side of the central meridian, we are now 300 kilometers on either side of the central meridian. So it makes the the application of this projection in a far larger area. So you don't have to divide the country up into 9 zones. Here you can divide them up into 4 zones and get the same. Accuracy, slightly different. You're not getting the same accuracy at the same scale, but depending on your application, this could be useful. So scale is consistent over a larger area. Lambert's conformal conic is where we want a projection nationally. So I want to show something across the whole country, and it has to start in the east and west, north, south. And Lambert's will preserve angles and distances to a lesser degree, shape and area. So if you're looking at traditional cadastre mapping, where we have the distance and direction of the sides of your land parcel, your cadastre, you could store that within Lambert's. But be aware that the area that you're calculating potentially in Cape Town versus the area you're calculating in Mbombela might be slightly different, because it's not maintaining those areas. In this case, we use the parameters of a central meridian of 24 degrees east, and we have 2 standard parallels. We spoke about those as the conic projection having the cone touching the earth, and then where it actually intersects the earth, we will have these 2 standard parallels, one at minus 24 and one at minus 33 degrees. The last one I want to touch on from a pure projection point of view is Albers equal area, and this is very similar, can be used nationally, but what Albers does is it maintains area. So if you're looking at the size of different features across the whole of the country, then you would use Albers equal area. Central meridians and the standard parallels are exactly the same as Lambert's, but you're using a different projection system. Now, I know I highlighted some of the issues with the Webb-Mercator projection a bit earlier, specifically when it came to area and length, but let's look at this. So it's become the de facto mapping standard for web-based applications such as Mapbox, Esri, MapQuest, OSM, Google, because many people are not printing maps anymore, but they want to have a projection that works globally. So this is used globally, and this works. But as I touched at the bottom, it's a non-conformal projection, and be careful and do not calculate attributes. So do not go and measure your distance and your area in Webb-Mercator, because there's a chance that it's not going to be correct, because it's not conformal across the whole globe. So use it for visualization, use it for rendering, but maybe if you're trying to calculate those areas in the correct projection system. Just something to be aware of. Recently, there was a proposal to update our large-scale mapping projections to move away from the Westings, Southings, the Gauss-Kruger. So if you look there, the status quo at this point in time is Gauss-conform projection with the 9 zones, and it's left-handed projection system. As I say, it's a Westings-Southing. And here the maximum distortion is about 132 parts per meter. So it's a very accurate projection. And we started looking at different options. CDNGI led this initiative to find an alternate for this projection system. So both looking at a projection system and looking at, do we want to keep the negating and the swapping of the XYs, or do we want to leave them as they are? So some of the options is to just move to a transverse Mercator. It has the same accuracy requirements, but we now work with a right-handed coordinate system and not a left-handed coordinate system. So we move straight away. It's no issues with accuracy, but the X's and Y's are now swapped, and we've removed the negatives. If we wanted to go to UTM and use the 6 zones, or say 6 degree zones or 4 zones, you'll see that the error goes up to 786 parts per meter. So there's definitely, you're losing something when you open up the zones using the UTM. There was also the option of going for Lambert's conformal conic, where we use 3 degree zones, and that we do not have a projection for the whole country, and that's at about 191 parts per meter, versus one with 4 zones, which would be 340 parts per meter. So there's different options that are being looked at. None have been adopted. There's a lot of work going into understanding the implications of this and making sure that we do not lose the accuracy. We have a very accurate cadastral base, and we want to make sure that we maintain that coordinate accurate cadastre. But there are things on the horizon that we have to update and stay in line with new techniques and new approaches. So this is something that you potentially will see in the future. So take-home message on both South African projections and some of these recent proposals that have come through have been: what projection system should we be using if we're mapping features at a scale of less than 1 in 50,000? At the moment it's Gauss conformal, and a lot of people use transverse Mercator. But is that going to be acceptable in the future? Because we work across those 9 zones of 200 kilometers wide, and sometimes that becomes a problem. We have 2 nationally accepted projections: Lambert's equal area and Albers conformal conic. And those are, depending on what you're trying to do, maintain area versus maintain distance and direction, depending on what you want to use. The telco industry used UTM. And a lot of the planning tools that are used for wireless clutter, we talk about clutter analysis, or wireless propagation analysis, uses UTM. And they've standardized on that, and there's nothing wrong with that within the application. So, depends on what you're trying to do. But be aware of the options, be aware of the limitations of each one of those options, and how you're going to appropriately apply it. One of the big things we all get caught out with one day is that we'll be given a data set with no metadata, which is a crime in its own right, and also no projection defined. And we don't know where it is. So we struggle to understand how to place this and how to define the correct projection. And this is not a science. This is a lot of hard work and experience that you're going to have to apply. My approach has always been is you need to at least know where the map is. So if somebody says to you, here's a map of Florida Lake in Johannesburg, and I want it mapped, or here's my data, you should go to another piece of software, find where Florida Lake is, and start doing some queries on different projections to see what the coordinates will be in X and Y. So is it in Lambert's, is it a UTM, etc., and then go and compare them against the coordinates. So that first comment, what does the data represent? Is it a road network in Florida? Where is it? Okay, it's in Florida. So I roughly know where it should be. Then I can go and look at projection parameters for that area from other data sets and start saying, oh, okay, but it is minus 2,700,000. Okay, that's from the equator. Potentially that could be transverse Mercator. This is not as I say, a science. You need to have done this, and it's a skill that you need to learn, that you can understand. And when you read the coordinates that are given to you in a data set, that you get to understand roughly what those coordinates are. That you aren't stuck with this data set that hangs in space, as I like to call it, and you're not able to place it on the Earth's surface, and it could be a false northing, it could be a false easting. In the time where we used to get a lot of data from CAD systems, people would have localized coordinate systems, and we would need to know the origin of that coordinate system and how we can apply that. I'd like to go into this in far more detail, but I think that's a topic for another day, is to explain how we would tackle CAD drawings and some other data sets. But just to keep in mind, know where the data is, sort of roughly understand where it is in context of central meridians and the equator, and what the value should be. In the case of Pretoria, is it been captured in 29 instead of 31 as an example? That we know that. So is it negative or is it positive? It's one of those questions you can ask. So in summary, just some closing thoughts on what we've gone through in these 3 videos. And the one is choose the most appropriate projection. And sometimes it's not just a choice, it's official. You have to use a given projection for a specific thing, and you need to understand, what are you trying to look at? What scale map are you working with? Where's the location of the data? What is the application of the data? What are you trying to achieve with the data set? So when you have the opportunity to pick a projection, you need to be able to justify your decisions based on this. It's a 1 in 50 or 1 in 40,000 data set. It was in the Western Cape. It is used for agriculture. Now I understand the context of what I'm trying to map, where it is in terms of South Africa, and how I can apply it. And then critical. I've given you some examples of the area and the distance in that example at Summerstrand, that when you are extracting attributes from a data set, make sure you're using the correct projection. Because if you are using something like Web Mercator and doing area or distance in a place like Gqeberha, you're going to get wrong answers. And it's not that they're wrong, it's that as soon as you've got an area field in your data set, you're not saying it came from a Web Mercator projection, and people will think it's maybe coming from something else. Once again, metadata is crucial and important. Beware of the limitations of projections. What are the different projections? Do they maintain area? Do they maintain distance? Do they maintain direction? So that you understand the application and how and why you would use a specific projection. And there's legal implications. You cannot map something at a scale of less than a 1 in 50,000 in South Africa, which has legal connotations, i.e. cadastral boundaries or parcels, if it's not in our Gauss-conformal projection at the moment. And that's just the given part of the Professional Land Survey Act, and that needs to be abided by. And then sometimes when it comes to datum transformations and picking datums, the software can get quite intelligent and can pick them, but make sure it's picked the right one. Remember I said that if you're doing a visualization, you could do the Cape to Hartbeespoort transformation, but if I wanted to make sure my cadastre was in the right place, I would prefer to be using an NTV2 grid. So be aware of that the software has become very good at picking your projection from your metadata, doing the right transformation, but make sure you understand what it's doing so that you can defend those decisions it made and that you are aware of the limitations of what it's done. So it would be time for questions now, and however, we would have to do this in a different way. But thanks a lot. Thanks for your time. And I hope you got an insight into projections and the implementation and application in South Africa. And we'll be following this up with more videos like this on different topics in the future. Thank you.